In this section, we are going to discuss clouds, fog, and precipitation and their impacts on air quality. Clouds, fog, and precipitation can affect PM 2.5 formation, chemistry, and dispersion. PM 2.5 can form through aqueous chemical reactions. Clouds and fog impact diurnal temperatures and vertical mixing. Forecasters look for clouds and fog because they influence the diurnal temperature pattern and the resultant vertical mixing. Falling precipitation can enhance vertical mixing and dispersion, thus lowering PM 2.5. So how do clouds form? Clouds form when the air becomes saturated. Air can become saturated in two ways. One is by adding water vapor to the air through evaporation, and the other is by cooling the air. There are many processes that can cool the air. Two main processes are rising motion and the air becoming in contact with a cooler surface. Examples of rising motion include an aloft trough of low pressure, daytime heating creating convection, fronts, and orographic lift, such as air being forced up a topographic boundary such as a mountain range. Another way to cool the air is when the air comes in contact with a cooler surface. This can be either land or water. So how do we observe clouds? Well, aside from looking out the window, we can use satellites to evaluate clouds on a large scale. In this image on the screen, we are looking at an example of visible satellite imagery. Visible satellites have a resolution around 1 kilometer and are particularly useful for identifying the extent of fog and low clouds. However, visible satellite imagery is only available during the daylight hours. Clouds can also be observed using infrared satellite imagery. Infrared satellite imagery is available 24 hours a day and can be used to infer cloud altitude by the temperature of the cloud. Recall that temperature decreases with altitude. Therefore, the higher the cloud, the colder the cloud top, and thus the whiter the cloud will appear in the infrared satellite imagery. The warmer the cloud top, which are lower in the atmosphere, will appear more gray. An enhancement can be placed on the infrared imagery to better distinguish the cold or high clouds and the warm or low clouds. Infrared satellite imagery does have a coarse resolution, around 4 kilometers. In the example on the screen, we can see the same area as was shown in the visible example earlier. However, from the color, we can tell that the clouds over the Pacific Northwest are low-level clouds because the clouds are more gray in nature. This was not easily apparent in the visible imagery. Aside from satellite imagery, we can obtain information about clouds and cloud cover from the station plot, which has been discussed before. Total sky cover is depicted by the amount of shading in the circle. In this example, since half of the circle is shaded, the sky cover is considered to be partly cloudy. If you look on the bottom of this example, you can see the other denotations for cloud cover. A completely empty circle is considered clear. A quarter-filled circle is considered few clouds. The half-filled circle, which we already discussed, is partly cloudy or scattered cloud cover. 3/4 full is mostly cloudy or broken. An entirely shaded circle is considered overcast. If there is an X through the circle, there is considered to be an obstruction, fog, smoke, etc., impairing visibility, and no cloud cover measurement is taken. Now that we have discussed clouds, let's look at fog. Fog is essentially a cloud on the ground. Fog slows heating of the ground, which limits daytime vertical mixing. There are 4 types of fog we are going to discuss: radiation, advection, upslope, and evaporation. The first type of fog we are going to discuss is radiation fog. As previously mentioned, the ground cools at night as long-wave radiation is emitted to space, and the air next to the ground cools more than the air aloft. The air near the ground becomes saturated, and fog can form near the ground. The fog then deepens from radiative cooling from the fog top. Solar heating during the day warms the ground and causes the fog to burn off. The ideal conditions for the formation of radiation fog are a moist ground and clear skies and calm winds. The second type of fog is advection fog. Advection fog forms when relatively warm air moves or advects over a cold surface. The cold surface cools the air. If saturation is reached, fog will form. This type of fog is common on the West Coast due to the advection of air over upwelled cold coastal waters. The image on this screen is an example of advection fog from San Francisco, California. If you look closely, you can barely make out the Golden Gate Bridge. The third type of fog is evaporation fog. Evaporation fog forms when warm, moist air mixes with colder air, causing the air to become saturated. Examples of evaporation fog include when you exhale on a cold day. You have what appears to be a cloud coming from your mouth. If you see what appears to be steam coming from the pavement on a hot day just after it rains, this is evaporation of water from a relatively warm, wet surface and mixing with the colder air above. Smokestack plumes are another example of evaporation fog, as well as contrails from a jet engine. Finally, the last type of fog is upslope fog. Upslope fog occurs when moist air flows up along a sloped plain, hill, or mountain. The rising air expands and cools, leading to an increase in the relative humidity until the air is saturated, and then a cloud forms, or in this case, fog. The example on screen shows a schematic of the formation of upslope fog. You can see the air being forced up the hill, and the cloud develops as the air becomes saturated. The second example is a real-life example pictured from a mountaintop. Finally, let's talk about precipitation. Falling precipitation can actually remove some pollutants from the air, mostly the larger particles, PM10. Falling precipitation also creates vertical motion in the atmosphere, which can help to increase dilution. Precipitation can increase humidity, leading to an increase in secondary PM 2.5 formation through those aqueous chemical reactions we discussed earlier. From the station plot shown on the screen, on the left side in the middle is where the present weather observation is denoted. In this example, the present weather that has been observed is thunder with no precipitation. If you look towards the lower left-hand corner of the image, you will see the denotations for other weather phenomena, including precipitation, such as rain. So what do forecasts need to look for? Well, fog can lead to enhanced secondary PM 2.5 formation and impact vertical mixing and PM 2.5 dispersion. Again, winds are usually calm when you have fog. There's high humidity, increasing those aqueous chemical reactions. Clouds during the day lead to a decreased vertical mixing and thus a decrease in the PM 2.5 dispersion. Precipitation, if heavy enough, can lead to some decreases in PM 2.5 due to increased vertical mixing and deposition. However, it is not very efficient at removing the particles if the precipitation is light. In this section, we have discussed clouds, fog, and precipitation and their role in the impact on air quality. Clouds decrease photochemical reaction by limiting the amount of sunlight. They act as a blanket, blocking the sun. Clouds and fog increase the aqueous chemical reactions, increasing the secondary PM 2.5 formation. Convective clouds, however, show that there is vertical mixing in the atmosphere and can actually vent pollutants out the top. Clouds and fog reduce daytime heating and nighttime cooling, impacting vertical mixing. With clouds, there is generally an increase in nighttime mixing and a decrease in daytime mixing. Precipitation can increase deposition and removal of PM 2.5 if heavy enough and if the vertical motions are strong enough.